So we don't have many days left for the course. This is today, 21st. And next week, like I said at the beginning of the semester, there's an international conference. And I wish you to go there and learn something. And because of that, we don't need to do any lecturing on next Monday. But next Wednesday, you can use the course time to go to IB building. So in this particular time period, there are 2 different sessions. So the first one is about AI technology and also vision technology. So there are several papers in this time period. And it's in the room of IB 201. Okay, you can go, just walk in and sit down, listen to the presentations. And there's another room. If you scroll down, I can show you the web page later on. You can scroll down down to here. At the same time, another room, IB 202. Here's a room about micro manipulation and also some unmanned vehicles. So you can decide, okay, which room to go. So fine, please prepare a way for them to write their, a short report about this participant. So just please go. Maybe you figure out a way for them to sign up. So when there's only a few talks. Like for the first room, there are 4 presentations. You can look into those topics and see if you are interested. Or the other room, also 4 presentations. So each of them is only 20 minutes. So that's for next week, next Wednesday. Okay? Please write emails to remind them. And maybe you can show them the details. Okay? Just the details about this time zone. Okay? So back to our course. I know you may not be knowing what to do for the project. I wish you can. Did they link to our TA?
Yes.
Okay. So please find time to talk to our TA. And I'm proposing that you guys can give a short presentation on December 5th, just to propose what you plan to work on. So on that day, I can comment on what you plan to do. Maybe something should be modified a little bit. Based on my comment, you could kind of figure out what to do. And if we do final presentation on 14th, that only gives you 1 week. That's too short. So I recommend that we do it on 21st. But one thing you need to be aware, 21st is the week of your final exam. So if we do final presentation on the final exam week, that means you may be having some exams in other courses. So you can let me know if you want to do this, or do we move on to another week? We can do the presentation on 28th, or the Monday right here. So let me write it down so you guys can think about it. So plus 7, that will be 20, 26, 27, 28, right? So maybe we can use this date for final presentation, or this one. It's really up to you guys. You guys are here, so you guys can make a decision. Other people needs to follow.
So, do we vote now?
Yeah, we can do it. Do you want to present on which day? Okay, So let's do a voting.
Sir,
Yeah, go ahead.
how long?
How long is the presentation?
8.
Yeah, I think 5 minutes.
Oh,
Short presentation.
Oh, okay.
Because we have how many teams? 5, 6?
6.
We have 6 teams, and if you give 5-minute presentation, I give you 5-minute QA. That's 10 minutes, and 16. That's an hour. So it's doable in 26. And the proposal can be even shorter, like 2 or 3 minutes, just to talk about what you plan to do and how that arrangement is related to this course. Like you propose to focus on one of the mechanical component. You are planning to do finite element on that part. You guess the stress concentration could be somewhere here or there. And as a designer, I could be changing the dimension of something. For example, the thickness of something or diameter of something. So after the calculation, if it's not safe enough, I could enlarge some particular portion of the design in order to increase the safety. Or if it's too safe, I can reduce weight, something like that. But when you propose, it's like you haven't done anything yet. You propose by your own guess or by some idea from the course. And within the 2 weeks, you will complete what you plan to do. On the final presentation, you present the results. Are you ready to vote?
yes.
Okay. So now we are planning. If someone is late, we are voting for the date of your final presentation. On the 19th and 21st, that's the week of your final exam. If you don't want to do it on final exam week, we can do it a week later, on the 26th or 28th. So it really depends on what you plan to do. So who wants to do 21st? Okay, 3. Okay, who wants to do 26? You're thinking, okay, 1, okay. 28?
Oh, no.
You want to do it? Okay, 2.
Oh, no, I 28.
You're 28, okay, so 1. So 28, 2. Who didn't vote? You didn't vote.
I think
28. My friend.
okay, 28.
You 28. You didn't vote. He said 28, okay. 28 wins. Okay. It's okay? 28 okay? 28 okay? Do you need to find some more people to come and vote? 28 okay? Okay. So we do final presentation on 28. Okay. He's here. He can vote. Hello. Very important, you're a key person. So we have a final presentation date. Originally, we should do it on 21st, but that's the final exam week. So now we are voting, should we move on to the next week? Do you prefer this is Wednesday, Monday, do you prefer 21st or 26th or 28th? Pick one. Which one do you like? You like, okay, 28 is the winner, okay. Okay. So we are not doing any course on these days because this is final exam week, no course. We just do final presentation on 28. So that means we only have today, next week, the 7th, 12th, and 14th. Okay, so only 8 hours left for the course. In that case, I guess I shouldn't use handwriting notes because that takes a lot of time. Let's use PowerPoint files. I do have some PowerPoint files, and I can share with you something that is related to the course. And today I can talk about gears. Oh, I only have 29% of battery. Let me use here.
We already prepared last time.
28. You vote 28. Okay, okay? Okay, good. She has no idea what that means. Okay. So you may have learned something about gears in another course, like a design of mechanism or kinematics or dynamics. But in this course, we're not going to review what you have learned in the past. Or maybe you didn't learn about gears in the past. That's fine, because I don't have exams for this part. So if you miss anything, if I go through really fast, that is because that may not be the major scope for this course. And if you're interested, you want to look into related topics, if you have a book you can read through. Or gears have been introduced in many different courses. So I'm not going to, okay, you may need to know the terminologies. Okay, for gears that is connected face to face, and the teeth are like connected like this, they are called the spur gears. Okay, and if the teeth are following a helical curve. Helical is like a spiral curve. Those curves are spiral curves. Then it's called helical gear. For this one, it looks like a shape of umbrella, because in Taiwan, in Chinese or Taiwanese, we call them the umbrella gears. But in English, it's actually bevel gears. The shape of the gear is in a cone. It's like two cones connect with each other. Okay, and the teeth of the gears, it was built on top of the cone shape. You can see it's like a cone, okay? And for this kind of gear, you don't see anything right here. It's basically a figure indicating so-called the pitch circle, but actually there is a gear. And it's called a worm gear because this guy looks like a worm, okay? And this kind of mechanism is commonly seen in a fan, an oscillating fan. So if you have no idea what's going on, you can YouTube. Oscillating fan wonky. And yeah, you can take a look at this one. So right here is not very close. Let me see if I can find another one that looks actually this is a wonky. This guy and this guy, they are a set of gears, but this one looks like looks like a shape of a screw, and the white circular thing looks like a gear, and the teeth actually are like a pair of gear shape and a screw shape, and they for gear sets that look like this, they are called the worm gears. Okay. Anyway. Now you know the names. And we start with the spur gear, and there are several terminologies. The most important thing is this circle right here. It's called a pitch circle. So what is a pitch circle? Basically, there's a we call conjugate motion. When two rigid body connects with each other, and motion of one object will affect the motion of the other object. It's a kind of conjugate connection. And the conjugating gear basically has a pitch circle as well. Mathematically, when we design the gears, we wish the pitch circle of this one has connection with the pitch circle of the other one, and they have a single contact point, so like a tangent to each other. Okay, so how people design gears starts with the pitch circle. So like right now we want to transmit some rotational motion to somewhere else over there, and they are not in the same, they are not at the same, having the same axis. How can I transmit this kind of rotational motion to the other place? We can put a bunch of gears, and every gear connects with each other and having a conjugate motion between the teeth. But how do we know what size do we use? So at the beginning, they draw pitch circles. So it's like an imaginary circle right here, and there's another pitch circle next to it. Those pitch circles tangent to each other, and they make sure, okay, at the end, I have a rotational axis right here, and I have another rotation axis right there. They are right at the location that I want. Now, when I have a proper design of the rotational circle, the pitch circles, then there are several parameters to be defined. And those key parameters defines how this geometry look like. But if you really want to know how to design gear, it's not the scope of this course. You need to take a course by Professor Shi Yipei in our department. Professor Shi. I think is maybe spelling like this. So if you are really into if you are really into gear design, oh, not this one. Yeah. She's an expert in gear design. Yes. Yi Pei Shi. It's actually this character. The pronunciation is Shi, okay? But the meaning of this word is stone. Okay. This character is stone, okay? So Professor Shi, she's a gear design expert. You can take her course, then you know how exactly to design a gear. But I'm not going to cover those in this course. You just need to know some information about the gear. Like we sometimes treat a tooth like two parts. The upper part is called, this is a face, and this is called flank. So this is just names indicating where they are. And the height from the pitch circle to the top of the face is called the addendum. And from the pitch circle to the bottom of the flank is called the dendum. Okay? Basically names. And you know, the geometry of a tooth remains the same from one to the other, and they are repeated geometries. So the width between each teeth is the same. That's why there's a very important term right here. The distance, the circular distance, or the arc length from one edge of one tooth to the neighboring one represent this arc length is called the circular pitch. So if there are 20 teeth in this gear, then the circular pitch equals to the parameter over number of the teeth. Okay? And those two parameters are very well used in all the calculations. That's pretty much you need to know at this point. So, if I'm planning to give you exams, those equations are the equations you must memorize. But since we're not doing it, so just take a look. So n is number of teeth. D is the pitch diameter, the diameter of the pitch circle. So n over d, n over small d, we call diametral pitch. So it's like how many teeth per unit length. And in so many manufacturing information, they use inch. So in many cases, it's teeth per inch. Okay? And the inverse of it is called the module. In Taiwanese, in Chinese, it's 模数. So a module defines how the teeth look like. So usually they have the cutting tools or the manufacturing tools that were designed in certain given module numbers. They don't change the module numbers by their own will. They usually pick up the one and then use it to create gears. Okay? So usually what you pick up at the beginning is to pick up the module. And once you pick up the module, you will figure out how many you have your pitch circle diameter. You have module, then you know how many teeth you have. Okay? And capital P and small p are different. The capital P is the diametral pitch, basically number of teeth over the entire over diameter. But small p is the pitch, is the arc length. So the unit is in the length unit. Okay? Anyway, you're not doing any calculations, just for you to know. Okay? So I'm going to move on very quickly because I want to focus on what I want you to understand. This is about the involution profile, and that is how the gear is being, the shape of the gear, of the teeth is being defined. Okay, this is very important view here. So this is representing a set of gears, and as you can see, this circle and this circle are tangent to each other, and you can see there's like a tilting line right here. So the smaller circle is called the base circle. The other one right here is also another base circle. And this tilting line is normal to or tangent to the base circle. And so here is normal. Okay? So what does this line mean? This line means this line represents the direction of the pressure. So over here, it's actually making a drawing of the teeth, the profile of the teeth, the tooth, and this curve is representing the profile of the tooth right here. Okay, so imagine here is one tooth, here's another tooth. Okay, so they are connecting with each other, and their the normal of that connection is always passing through this line. Okay, so as this gear is rotating, like in this way, this gear goes to in this position, and this gear goes to this way, and the connection point is always on this line. Okay, so from here you can tell this conjugate motion was defined in a certain way that whenever a tooth connects with the other tooth on the other side, the connection points lies on this line. Okay, and as the conjugate motion moves on, that tangent point is always on this line. The involution profile was designed in a certain way, so this connection point is always on this line. So this is a very important information for us, because that ensures us that the force between two gears are always following this. The force between the two gears are always following this line. Okay? So when we calculate how much force is being applied from one side to the other side, the force is always following this line. So for us, when we do calculation about how one tooth carries the load, what we're doing is we have a tooth right here, and we know the force is coming this way. And here we call the pressure angle. So for this particular tooth, we know the force comes this way, and this tooth is like a cantilever beam. It's like a beam hanging from the base of the gear, hanging right here, and the force coming along a particular angle, and it's pushing the tooth. So the tooth is under some kind of bending. Later on in the force analysis, I will tell you there's actually a model describing how this tooth is carrying the load. And over there, people have developed a bunch of design equations for the failure of the tooth. Over there, it's still following a concept. Is the load smaller than the strength? Basically, same idea. The tooth is carrying some kind of load from the other side. Is it smaller than the strength? If it's not, then the load is too large. If the load is smaller than the strength, then the tooth won't fail. Okay, that's the idea. Okay, so moving on to the focus of this course. There are some mathematics behind all kinds of gears, but that will involve a lot of geometrical relationship between angles and length, but I don't think I should introduce those, because like I said, the purpose of this course is for you to know what's going on, but not to truly do calculations. So here is just a quick glance. What happened? When we are dealing with so-called a helical gear, the profile of the gear is not parallel to the gear itself, not parallel to the cylinder. It's having a tilting angle. So that angle is called the helix angle, right here. Helix angle. So this angle is talking about how this line is tilted on top of a cylinder to form a helical curve, basically a spiral shape or spring shape. Okay, so if you have a cylinder, if you draw a line straight, then this is following the direction of spur gear. So a spur gear could be like this, right? Straight. If you understand, the spur gear is having the tooth shape straight, parallel to the cylinder. But if you start to tilt the line by a little, then you are creating a helix angle. So that tilt forms a non-straight line. It's like a curve. And if you tilt it so much, it's actually forming a spiral shape. But for helical gear, usually it's not that large. It's like a tilt a little bit. So when you see a gear shape like this, it's forming a kind of helix at the surface of the cylinder. Okay, and when people make a drawing, it looks like that. But so when the tooth profile is like that, how can we do calculation? Because the tooth profile is so complex. So what's happening is, if you view the helix, the helical tooth along this direction, And if you view from this angle, this helix angle from here to toward the tooth, you will see the tooth shaped like this. And perpendicular to the way of your view, if you study the tooth on this plane, the tooth right here is actually like a spur gear. So it's like if you view along the helix line, it's just like a spur gear. So when you view along this helix angle, if it looks like a spur gear, then the calculation for the spur gear can be used along this direction. So this is why some equations that was shown earlier can be used here, because these calculations will be used along this plane. Then applying the helix angle, they can study what's going on along this axial direction. Okay, but for details, like I said, I'm not going to take too much time. Okay. Okay. So this is how they cut the gear. This is like a cutting. So by the way, what is a pinion? When you have two gears, one is smaller, one is larger. The smaller one is called a pinion. So you sometimes hear a term, pinion and gear. Pinion and gear means you have a set of gears. The smaller one is the pinion. The larger one is the gear. And sometimes people say pinion and rack. What is a pinion and rack? This is pinion and rack. Gear that has infinite large radius, that is a gear profile in a line, and that is called a rack. Okay, so if this is a gear that has infinite large radius, this gear is larger than this one. So this is a gear, then this is a pinion. And they call this kind of gear a rack. That's why people sometimes call pinion and rack. Okay? That's for you to know. Otherwise, sometimes when you read about gears, you see those terminologies, you have no idea what's going on. Okay. Okay. So for bevel gears, what I would like to tell you is I need to get rid of those two first. Okay? So for bevel gears, the teeth lies on a cone. This is a cone shape. Okay? And if you have good imagination, right here, the tooth may look like this, okay? Right? And the other side has another tooth like this, okay? If you can tell. So if you focus on this part, you can see this edge is a straight line. The contact line is a straight line, and two teeth are connecting with each other. If you focus on this area and focus on this perpendicular line, you can imagine these two teeth are actually having similar conjugate motions like a pair of spur gears. So what I erased earlier actually were the set of so-called imaginary spur gear or virtual spur gear. So the motion between two bevel gears right at the conjugate motion point are just similar to two sets of spur gears. So some spur gear calculations could be used to describe the motion in between, but you have to use the virtual gear parameters. Okay? So just for you to know, even bevel gears are a bunch of teeth lying on two cones in a very complicated geometry, but when they connect, the teeth themselves are still acting like spur gears. Okay? So maybe we can see if we can find something on bevel gear teeth, maybe. Okay, so if you look at this, if you look at these two, right at this position, if you draw a perpendicular plane along the edge of the cone, the teeth between them are just like a spur gears. They just make a wrap on top of the cone shape. Okay? So calculation-wise, they still use spur gear equations to calculate the shape of the bevel gear. Okay? So let me move on to, I think that would be too much for both. Because all these are just informations about how the gears look like. But the key of this course is actually about how the force is being transferred from one side of the gear to the other side of the gear. So I need to talk about, let me see, this one. So now you realize what we actually cares about is the direction of the force. So this is a pair of spur gears, and this tilting line is the pressure line, and this is the pressure angle. We're sure when two teeth connect with each other having a conjugate motion, the force lies on this line. So if you draw the free body diagram of each gear, you will end up with two diagrams right there. The top one is the gear where you have a external force from the gear A pushing the teeth right at the tangent point of the pitch circle, as shown right here. So this external force represents how the teeth that is pushing the teeth on gear B, and it's following this direction. Okay? Since you are sure there's a pushing force right here, there must be some kind of reaction force somewhere at the center axis. And the only way to have force balance is to have the same force lying on the same direction, along the same direction, but parallel to each other, but opposite direction. So force balance matches. But these two forces forms a couple and generates a counterclockwise moment. So in order to balance it, there must be a clockwise moment that is balancing the moment generated by the couple. So this clockwise moment is generated on top of the axis. So a pair of gears not only generates some reaction forces at the center cylinder, but also generate a torque right here. So in the future, if you try to analyze a cylindrical system and you have gear sets, you need to realize some other forces that is being transmitted from other gears to the gear on the current cylinder you are analyzing. There must be some kind of reaction forces right onto the center cylinder, and that direction needs to be studied carefully, and also there must be some kind of torque, generating some torque. Okay? So that's the force balance on the gear B by itself. How about the gear A? Similarly, if we focus on gear A, there is a corresponding force right here. This force is representing how the teeth right here is pushing the teeth right here. And it's acting on this tangent point. Similarly, we should have a reaction force right here pushing along the parallelly on the center of the gear, but different direction. So you have balance of force. Again, this force couple will generate a counterclockwise moment. So at the center, there must be a reacting clockwise torque to balance the moment. So that's why you have a free body diagram like this for gear A. Okay? So in order to let's say you put a motor on one side of the gear, and in order to make the motion to initiate this rotation, the motor needs to have certain power. And since there's a reacting torque right at the center, you can use that to calculate how much power you need to really spin one set of the gear, and that will push the other gear to rotate as well. So the calculations at each gear is also related to how much power you need for the motor you use. If you have a very huge gear, maybe the reacting forces between them are large and leading to a really large torque. In order to make it rotate, I need to overcome the torque in order to make it rotate, right? So if I have a huge gear, I may need a larger motor. If I have a large gear but I have a very small motor, how come the small motor cannot drive it? Because there's already a reacting torque in between. If you cannot overcome the torque, you cannot drive it. Okay? So the main focus of the mechanical design in gears are about the forces. And over here is just a simple demonstration of how the forces are acting on each side of the gear. Later on, those information will be useful for the tooth strand analysis. So I will talk about that on Wednesday. Okay, I can share with you the slide, but like I said, there will be a lot of slides being skipped. If you're interested, you can look into them, you can read the book. Otherwise, this is just for you to know. Okay, that's it for today. If you have questions, you can stay. Otherwise, we can go.